On January 11, 3E Atlas is believed to have the ability to self-fragment in a way that allows its pieces to enter orbit around Jupiter. This interstellar object is predicted to have an exceptionally rare encounter with Jupiter in March 2026, during which the trajectory of 3I Atlas exhibits non-gravitational acceleration that cannot be satisfactorily explained by conventional ice sublimation, while also showing an unusually high level of precision as it approaches the planet's gravitational boundary. For this reason, scientists have proposed that if during this event 3I Atlas is indeed able to fragment in a manner that places debris into orbit around Jupiter, a process requiring velocity changes far beyond the limits of known natural phenomena, then such an outcome could be considered a potential technological signature. At the same time, 3I Atlas has also sparked intense controversy due to claims that it lost as much as 99% of its mass within roughly 90 days, transitioning from an object once estimated to weigh 33 trillion kilograms into an extremely lightweight structure without any observed signs of disintegration explosion or an accompanying debris cloud. This paradox undermines existing astronomical models and has fueled a confrontation between the mainstream fluffy comet hypothesis and alternative interpretations, including the possibility that 3I Atlas is an artificial structure or a light sail capable of adjusting its own density. These hypotheses suggest that Atlas's journey has not stopped, and that is precisely what we will explore next. The deeper scientists traced the motion of 3 Atlas back through space, the more the journey led their thoughts to the distant outskirts of the solar system, to a region known as the Oort cloud. This vast spherical halo of icy debris exists at temperatures only a few degrees above absolute zero, where sunlight is little more than a memory and thermal energy is almost entirely absent. In such an environment, 3A Atlas should have been locked in near-perfect stillness, its surface frozen solid, its materials chemically and physically dormant. Under these conditions, the physics of sublimation become extremely limited, because ice does not readily transform into gas when there is so little heat to drive the process. For typical comets, non-gravitational acceleration emerges only when they approach much closer to a star where solar radiation is intense enough to liberate molecules from the surface. 3I Atlas, however, displayed signs of acceleration long before reaching those warmer inner regions, creating a paradox that could not be easily dismissed. If outgassing were responsible, the rate would need to be surprisingly high for such extreme cold, implying either unknown volatile materials or a mechanism not accounted for in standard comet models. This placed researchers in an uncomfortable position because adjusting the chemistry to fit the motion of 3 Atlas required assumptions that stretched beyond what laboratory physics currently supports. The alternative, that the observed acceleration was not driven by thermal sublimation at all, carried even deeper implications. As models were refined, scientists realized that ignoring this extra push caused predictive errors to grow rapidly, turning precise orbital forecasts into rough guesses. To maintain accuracy, the influence had to be treated as real and persistent even though its physical origin remained elusive. 3. Atlas thus transformed the frigid silence of the Oort cloud from a region of passive storage into a stage for an active mystery where motion existed without the heat that should have made it possible. As the designation attached to 3 Atlas was refined, scientists began to realize that the label itself carried weight beyond simple cataloguing, because the prefix 3I marked a category that had only been entered twice before. The first interstellar visitor, known as Oumuamua, arrived briefly, and departed quickly, leaving behind questions but few opportunities for prolonged study. The second Borisov behaved much more like a conventional comet, displaying a visible tail, familiar chemistry and motion that aligned comfortably with existing models. 3 Atlas entered this lineage quietly, yet the behaviour of 3 Atlas immediately suggested a departure from both predecessors. Unlike Oumuamua, 3 Atlas did not vanish before careful tracking could begin, and unlike Borisov, 3 Atlas refused to settle into the role of a typical icy wanderer. The motion of 3 Atlas lacked the dramatic flares and obvious jets that usually announce active comets, even while the trajectory itself continued to drift away from gravitational expectations. This combination created an identity problem because the object did not fully belong to any known class, even as the classification system insisted on placing 3I Atlas somewhere familiar. The difference was not merely visual or chemical, but structural in behaviour, as 3 Atlas maintained a calm, almost disciplined motion that contrasted with the erratic personality often seen in small natural bodies. Every comparison highlighted the same conclusion that 3 Atlas was not simply another example along an existing spectrum, but a point that seemed to fall outside the curve entirely. By assigning the third interstellar designation, astronomers acknowledged rarity. Yet the unfolding data hinted at something deeper than statistical chance. 3 I Atlas was not just different in origin, but different in character, quietly suggesting that the category itself might need to expand, or that the assumptions behind the labels were no longer sufficient. When the orbit of 3 Atlas was finally resolved with sufficient precision, one feature stood out with unmistakable clarity, because the trajectory was hyperbolic rather than bound to the Sun. A hyperbolic path signals a traveller that does not belong an object arriving from interstellar space, with enough speed to pass through the solar system only once, before continuing onward into the dark. For most such visitors, this geometry implies a brief encounter, a flyby governed by chance where the object brushes past the Sun and leaves without forming deeper connections. 3. I Atlas followed this same geometric rule, yet the implications of its path quickly became more unsettling as probability entered the discussion. In a solar system vast beyond everyday comprehension, the likelihood that a random interstellar object would pass near any major planet is extraordinarily small, shrinking further with each additional constraint placed on timing and distance. Statistically, 3 Atlas should have crossed the inner system without drawing attention, its hyperbolic arc carrying it far from planetary influence. Instead, the projected motion of 3 Atlas revealed a course that brought it uncomfortably close to one of the most massive bodies in the system. This proximity did not violate physics, but it strained intuition because chance alone rarely produces alignment so precise within such an immense volume of space. As astronomers traced the curve outward and forward in time, the question quietly emerged whether the path of 3 Atlas was merely improbable, or whether improbability itself was becoming part of the story. As projections refined the future path of 3 Atlas, attention narrowed to a boundary that rarely becomes central in interstellar encounters, the gravitational threshold known as a Hill sphere. This invisible region defines where a planet's gravity temporarily overpowers the tidal pull of the Sun, creating a delicate zone where capture deflection or disruption can occur. For Jupiter, that region extends tens of millions of kilometers into space, forming a vast but precisely calculable envelope of influence. When the numbers were compared, 3 Atlas was predicted to pass astonishingly close to this boundary, missing Jupiter's Hill radius by a margin of only a fraction of a percent. In planetary dynamics, such a difference is almost vanishing, because small uncertainties normally accumulate into wide spreads over interstellar distances. Yet the approach of 3 Atlas aligned with the edge of Jupiter's dominance, with an accuracy approaching 0.2%. This level of precision is deeply unsettling because natural trajectories shaped by random initial conditions rarely thread such narrow corridors without significant dispersion. The mathematics suggested not a wide range of possible paths, but a constrained corridor, as though 3 Atlas were gliding along a boundary rather than wandering past it. Even small deviations in velocity or timing would have shifted the encounter far inward or far outward, eliminating the near miss entirely. As scientists absorbed this result, the encounter stopped feeling like a coincidence and began to resemble a moment balanced on a knife's edge. 3 Atlas was not entering Jupiter's domain yet. It was not safely distant either, existing instead in a liminal space where outcomes remain exquisitely sensitive. In that narrow margin, the motion of 3 Atlas transformed from a simple flyby into a question about how such precision could arise in a universe ruled by chance. As attention shifted from the trajectory of 3 Atlas toward the environment it was approaching, scientists began to examine the complex family of moons surrounding Jupiter. Jupiter is not only the largest planet in the solar system, but also a collector of fragments surrounded by dozens of irregular moons that tell stories of capture and disruption. Among these distant companions, Eupheme emerged as a point of quiet interest, not because Eupheme is large or bright, but because Eupheme occupies a fragile and unusual orbit. 3 Atlas was not aimed directly at Jupiter itself, yet the projected path of 3 Atlas passed through regions populated by these loosely bound satellites. Eupheme belongs to a group of retrograde moons' bodies that orbit opposite to Jupiter's rotation, signalling that Eupheme was not formed in place, but acquired long ago. These moons move on elongated, tilted paths shaped by ancient gravitational encounters that left them only weakly tethered to the planet. When orbital simulations were extended forward, Euphemia appeared repeatedly in proximity analyses because Euphemia's path intersected the broader corridor traced by 3A at last. 3A at last was not targeting Euphemia in any deliberate sense, yet the geometry suggested a rare opportunity for interaction. The significance lies not in collision but in gravitational influence, because even distant encounters can exchange energy when timing and position align. Euphemia reaches regions of space where Jupiter's grip is weakest, drifting slowly at the edge of stability, while 3 at last approaches at immense speed. This contrast creates a scenario where a massive fast-moving interstellar object passes near a small, delicately bound moon. 3 at last therefore entered a neighbourhood where minor perturbations can echo for millions of years. As astronomers mapped these overlapping paths, Euphemia transformed from an obscure dot into a reference point. Through Euphemia, the approach of 3 at last gained context, shifting the narrative from abstract probability toward a specific stage where subtle forces could leave lasting marks. As calculations refined the timing of the encounter, scientists noticed that the approach of 3 at last aligned with a particularly sensitive moment in Euphemia's orbit. Every moon around Jupiter experiences points of strength and weakness, and for Euphemia that vulnerability appears at apogee when Euphemia drifts farthest from the planet and moves at its slowest speed. At this distant point, Jupiter's gravitational hold on Euphemia is at its weakest, creating a state where even small external influences can have outsized effects. 3I at last was projected to pass through this region shortly after Euphemia reached that fragile position, a temporal alignment that immediately drew attention. In a dynamic system with dozens of moons, coincidences are expected, and astronomers are trained to treat apparent alignments with caution. The defense of coincidence argues that with enough moving parts, something interesting is always happening somewhere, and that probability alone will occasionally produce striking overlaps. Yet 3A at last complicates that comfort, because the interstellar object arrived not only near Jupiter, but near the precise orbital phase where Euphemia is least securely bound. This pairing of spatial proximity and temporal sensitivity tightened the probability window far more than casual chance would suggest. When models replayed the encounter thousands of times with slightly altered initial conditions, the alignment did not vanish easily. Small changes shifted details, but the broader relationship between 3 Atlas and Euphemia persisted as if the geometry itself were resilient. 3 Atlas did not require perfect aim to pass nearby, yet the timing appeared almost tuned to maximize potential interaction. This is where the narrative grows uncomfortable, because chance can explain proximity, and chance can explain timing, but explaining both together demands careful accounting. 3 Atlas seemed to arrive not merely near Jupiter, but near a moment of weakness within Jupiter's outer system. Whether coincidence or something more structured, the alignment forced scientists to confront how often randomness truly produces such delicate convergence in the vastness of space. As the encounter geometry became clearer, the discussion around 3A at last inevitably turned towards speed, because velocity defines what gravity can and cannot accomplish. At the moment of closest approach, 3A at last was calculated to be moving at roughly 66 km per second relative to Jupiter, a pace that is extreme by planetary standards but ordinary for interstellar space. At such speed, 3 Atlas carried enormous kinetic energy, and gravity alone could only bend the path gently unless very specific conditions were met. The critical comparison lies in escape velocity, because capture requires an object to lose enough energy to remain bound. Near the distance where 3A at last passed Jupiter, the local escape velocity was only a little over 2 km per second, meaning anything moving faster than that would inevitably fly past and never return. For 3, at last the gap between 66 km per second and 2 km per second represented a nearly insurmountable barrier. In natural systems, slowing an object by such a margin requires violent processes, yet none were evident along the path of 3 Atlas. Outgassing, which can gently push comets, operates at speeds measured in hundreds of meters per second, not tens of kilometers per second, and tidal interactions tend to stretch and fragment objects rather than break them efficiently. Even dramatic events like tidal disruption near a massive planet redistribute material, slowly producing relative velocities far below what would be required to cancel the motion of 3 Atlas. This creates a stark physical challenge, because for any fragment of 3 Atlas to become bound, An energy change on the order of 60 kilometers per second would need to occur in a very specific direction. The adjustment would have to be precise enough to reduce speed without eliminating the sideways motion necessary for orbit, a balance that leaves almost no room for error. In engineering terms, the tolerance is razor thin, while in natural terms such precision is almost unheard of. As simulations explored this scenario, gravity alone consistently failed to deliver the necessary outcome. 3 at last could be deflected, stretched, or even broken apart, yet the numbers refused to yield a natural pathway to capture. With every recalculation, 3 at last reinforced the same conclusion that speed itself was the gatekeeper, and that crossing this gate demanded more than the slow, indifferent hand of gravity could provide. As the mathematics were pushed further, the problem surrounding 3 at last became not one of possibility, but of precision, because slowing an interstellar object is only part of the challenge. For any fragment of 3 at last to transition from a fast hyperbolic passage into a bound orbit around Jupiter, the velocity change would have to be applied with extraordinary accuracy. The required adjustment was not simply large but exquisitely tuned, because the difference between escape and capture lay within a narrow window measured in just a few percent. At the distance of closest approach, Jupiter's escape velocity defined a hard threshold, and for 3A Atlas that threshold sat near 2 kilometers per second. Starting from roughly 66 kilometers per second, any successful outcome would require a velocity kick of more than 60 kilometers per second, delivered in a direction that cancelled most of the forward motion without erasing the sideways component needed for orbit. If the correction overshot even slightly, the fragment would plunge inward or be flung away forever, while an undershoot would leave it unbound and lost to interstellar space. In physical terms, this tolerance amounts to roughly 3% a margin that engineers associate with design systems rather than uncontrolled natural processes. Natural fragmentation events are messy, producing a spray of debris with a wide distribution of speeds and directions, not a clean, narrowly targeted adjustment. With 3 at last, however, the scenario demanded a correction that was not only powerful but selective, as though only certain pieces received exactly the right impulse at exactly the right moment. This is where the discomfort deepened, because gravity does not aim, and outgassing does not choose. Tidal forces stretch and tear, but they do so gradually imparting relative velocities that are far too small and far too chaotic to satisfy the constraints imposed by the equations. 3I Atlas therefore sat at the intersection of two incompatible ideas, one in which nature acts broadly and inefficiently, and another in which outcomes depend on fine control. As analysts reviewed these requirements, the language of coincidence began to strain, because chance can produce rare events, but it rarely produces events that must land within such a narrow band of success. 3 at last transformed the discussion from whether capture was unlikely to whether capture, if observed, would imply an intervention beyond passive physics. In that narrow 3% corridor, 3 Atlas challenged the assumption that every motion in the solar system is the inevitable result of blind forces alone. At this stage, the discussion surrounding 3 Atlas reaches a conditional boundary where conclusions are not drawn but criteria are clearly defined. The idea of a technological signature does not arise from belief but from the structure of the problem itself, because physics establishes limits that natural processes are not expected to cross. For 3 Atlas, those limits are set by energy, directionality and timing, all of which must align within narrow tolerances to produce outcomes that gravity alone cannot explain. If after the encounter with Jupiter, new objects were observed occupying stable or semi-stable orbits that did not exist before, the implications would be immediate and profound. Such an observation would suggest that fragments associated with 3 Atlas experienced velocity changes that exceeded what natural breakup mechanisms can reasonably supply. In that case, 3 Atlas would not simply be an unusual interstellar visitor, but a diagnostic event revealing behavior that demands explanation beyond passive dynamics. It is important to emphasize that this threshold is conditional rather than declarative. No claim is made that 3I Atlas is artificial, nor that technology must be involved, but only that certain outcomes would force a reassessment of current models. If those outcomes fail to appear, 3 Atlas remains an anomaly within nature, challenging but not overturning existing frameworks. What defines a technological signature in this context is not complexity or intention, but control. A process that produces large, precisely directed velocity changes in select fragments implies an ability to shape outcomes rather than merely react to forces. 3 at last, if shown to generate such results, would occupy a category distinct from known comets, asteroids, or captured debris. This approach mirrors the logic used elsewhere in science, where hypotheses are judged not by plausibility, but by their ability to survive specific tests. 3 at last therefore becomes less a mystery to be solved and more an experiment unfolding in real time. The presence or absence of these defined signatures will determine whether 3 at last remains a statistical outlier or becomes evidence that the solar system briefly hosted something fundamentally different. As the moment of closest approach approached, attention shifted from theory to observation, because 3 at last was not passing unnoticed through an empty system. A coordinated network of instruments had already been prepared, forming a quiet vigil designed to watch every subtle change in the environment around Jupiter as 3 at last moved through. At the centre of this effort was the Juno spacecraft, already in orbit around Jupiter, carrying sensors capable of measuring magnetic fields, energetic particles, and faint emissions invisible from Earth. Juno occupies a unique vantage point because Juno moves deep within Jupiter's gravitational domain, allowing Juno to observe interactions that ground-based telescopes can only infer indirectly. As 3 at last entered the region near Jupiter's outer moons, Juno's instruments were positioned to detect disturbances that might ripple through the system. Even slight changes in particle density radiation or dust distribution could signal that 3 at last was interacting with its surroundings in unexpected ways. On Earth, large observatories joined the effort, synchronizing optical infrared and radio measurements to track both 3 at last and Jupiter's satellite population. This global campaign ensured that no single instrument carried the burden of interpretation, because independent confirmation is essential when claims approach the limits of known physics. 3 at last was therefore not merely observed but monitored, framed by a web of attention that reduced ambiguity and increased confidence in whatever outcome emerged. What makes this campaign significant is not its scale but its intent, because scientists were not searching for proof of anything extraordinary. Instead, the goal was to establish a clear baseline so that any deviation could be recognized without hesitation. As 3 at last passed through this observational net, the solar system briefly became a controlled laboratory, prepared to record whether nature behaved as expected or quietly revealed something new. The implications of 3 at last extend beyond a single encounter, because the questions raised touch the foundations of how humanity searches for intelligence beyond Earth. Traditional SETI efforts have focused on listening for signals, assuming that technology announces itself through noise or light sent deliberately across the stars. 3 at last invites a different perspective, one in which evidence may appear not as a message but as behaviour that violates natural expectations. If advanced systems travel silently blending into the background of the cosmos, then close encounters become opportunities rather than accidents. 3 at last suggests that observation of motion timing and interaction may be as important as listening for transmissions. In that quiet shift of focus, SETI expands from searching the sky for voices to watching the sky for actions that cannot easily be explained away. The discussion surrounding 3 at last took a dramatic turn when mass estimates derived from observation began to change in ways that defied every familiar expectation in planetary science. Over a surprisingly short period, calculations suggested that 3 at last had lost the overwhelming majority of its inferred mass, shrinking from a body measured in tens of trillions of kilograms to something orders of magnitude lighter. Such a transformation would be extraordinary under any circumstances, but the absence of accompanying debris made the situation even more unsettling. When natural objects shed material at that scale, the process is usually violent and unmistakable, producing expanding clouds of dust fragments and gas that linger and scatter sunlight for months or years. With 3 at last, observers saw no such signature, because telescopes detected neither a growing coma nor a trailing cloud that could account for tens of trillions of tons of lost substance. 3 at last appeared to transition quietly, almost politely, from one inferred physical state to another, leaving behind no visible evidence of catastrophe. This silence created a paradox, because matter does not simply disappear without consequence, and conservation laws remain among the most reliable principles in physics. If 3 at last truly lost that amount of mass, then the surrounding space should have been saturated with detectable byproducts, yet measurements remained stubbornly minimal. 3 at last therefore forced scientists to confront a choice between accepting a dramatic violation of expectations or reconsidering the assumptions that produced the original mass estimate. The scale of the discrepancy sharpened the tension, because a loss of this magnitude is not a rounding error or a calibration glitch, but a fundamental shift in physical interpretation. 3 Atlas had been treated as a massive interstellar body during its early observations, in part because 3 Atlas showed little response to solar radiation that would normally push lighter objects off course. As later data contradicted that picture, the missing mass became less a question of erosion and more a question of whether the mass had ever been present in the first place. In this way, 3 Atlas transformed from a fading object into a conceptual problem where the true mystery was not what vanished but what had been mistakenly assumed to exist. For nearly 5 months, 3 Atlas moved through space under intense scrutiny, watched by a global network of observatories that tracked its position with extraordinary precision. During this period, 3 Atlas behaved with remarkable restraint, following a smooth and stable path that aligned almost perfectly with gravitational predictions. There were no sudden deviations, no detectable jets of gas, and no visible signs of activity that would normally betray an object interacting with solar radiation. This extended silence carried significant implications because in physics, the absence of motion can be just as informative as motion itself. An object that remains unmoved by radiation pressure must possess substantial inertia, and inertia in turn implies mass. Based on this lack of response, scientists concluded that 3 Atlas had to be heavy dense and resistant to subtle forces that would easily perturb a lighter body. The measurements during this phase were not casual estimates, but the result of painstaking analysis where positional changes smaller than a fraction of an arc-second were detected and corrected. Within those limits, 3 Atlas remained steady, reinforcing the assumption that 3 Atlas was a large solid object drifting passively through the outer solar system. This consistency built confidence because the mathematics of inertia are unforgiving, and the data appeared to confirm them. Yet this interpretation carried an implicit assumption that 3 Atlas was behaving naturally and transparently, revealing its true mass through its response to external forces. If that assumption were flawed, then the silence itself could be misleading, masking a different physical reality beneath an outward appearance of stability. 3 Atlas may have appeared inert not because 3 Atlas was massive, but because the forces acting upon 3 Atlas were balanced or suppressed in ways not yet understood. As later observations challenged the original mass estimate, this quiet period took on a new character. What once seemed like confirmation of solidity began to resemble a carefully neutral state, where motion and reaction were minimized. In hindsight, the 5 months of silence surrounding 3 Atlas became less a reassurance and more a question, asking whether stillness always means weight, or whether 3 Atlas was teaching observers that inertia can sometimes be an illusion. As the dataset expanded and newer measurements were layered onto earlier assumptions, the mass model built around 3 Atlas began to strain under its own contradictions. The original estimates had relied on a simple and trusted chain of reasoning where minimal response to solar radiation implied high inertia and high inertia implied substantial mass. For a time, this framework held together because 3 Atlas appeared to confirm it through calm and predictable motion. The problem emerged when later observations introduced forces that should not have been able to move such a heavy body. As 3 Atlas approached regions where solar influence increased, a measurable acceleration appeared subtle but undeniable and suddenly incompatible with the mass previously assigned. When these accelerations were inserted into the equations, the numbers no longer balanced because the same object could not be both extremely massive and easily pushed. This is where the collapse became unavoidable because physics does not allow selective obedience to its laws. If 3 Atlas were truly as massive as first believed, the observed acceleration would have been negligible, lost beneath the inertia of a giant body. Instead, 3 Atlas responded as though it were far lighter, as though the earlier portrait of solidity had been drawn from incomplete information. As researchers recalculated, the mass estimate fell dramatically, not by a small adjustment, but by orders of magnitude. 3 Atlas shifted from the category of an interstellar mountain to something closer to a lightweight structure, a change so extreme that it forced a re-evaluation of every prior assumption. The collapse was not emotional but mathematical because the equations themselves demanded consistency and refused to accommodate contradiction. What made this moment so unsettling was that neither dataset appeared flawed. The early silence of 3 Atlas had been real, and the later acceleration of 3 Atlas was equally real, leaving no easy way to discard either. The only option left was to accept that the model linking silence directly to mass had been incomplete. In this way, the mass model did not fail because of error but because of overconfidence. 3 Atlas revealed that a system can appear stable, while concealing properties that only emerge under changing conditions. As the old framework fell away, 3 Atlas stood not as a contradiction but as a reminder that even the most trusted models can collapse when a single object refuses to behave as expected. The turning point arrived when observations from the James Webb Space Telescope were added to the record because Webb was sensitive enough to detect forces that had previously remained hidden. Unlike earlier instruments, Webb could measure faint thermal signatures and subtle accelerations with extraordinary clarity, allowing scientists to isolate effects that were once buried in noise. When Webb focused on 3 Atlas, the data revealed a gentle but persistent push acting on the object, a force small in magnitude yet consistent over time. This acceleration was not dramatic, amounting to only a few meters per second over long intervals, but its significance lay in what it implied about mass. For such a force to produce a measurable change in motion, 3 Atlas could not be as heavy as earlier models suggested. When the numbers were recalculated using Webb's measurements, the apparent mass of 3 Atlas collapsed by more than an order of magnitude. The implication was deeply unsettling, because the same object that had once behaved like a massive interstellar body now responded like something far lighter. 3 Atlas no longer fit the image of a dense kilometre-scale mountain of ice and rock, but instead resembled a structure with far less resistance to external forces. This transformation did not require exotic physics, but it did require abandoning the assumption that brightness and stability necessarily correspond to bulk mass. What Webb effectively stripped away was not material but interpretation. The earlier picture of 3 Atlas had been shaped by indirect inference, by assuming that what appeared steady must also be heavy. Webb's data showed that this assumption could be misleading, because a light object can appear stable if external forces are weak or carefully balanced. As the recalculated values settled, the idea of a vanished mass gave way to a quieter explanation. 3 Atlas may never have been as massive as first believed, and the missing trillions of tons may have existed only in the equations. In this light, 3 Atlas did not shed a physical layer, but rather removed a conceptual mask, revealing that the object beneath was fundamentally different from what observers thought they had been tracking. The contrast between the early and later interpretations of 3 Atlas has often been described through an image that feels almost absurd in its simplicity, yet perfectly captures the scale of the discrepancy. At first, 3 Atlas was treated as a cosmic equivalent of a blue whale, massive, inert, and overwhelmingly dominant in its interaction with surrounding forces. Later, the same data set, when viewed through a different lens, recast 3 Atlas to something closer to a goldfish small light, and easily influenced by subtle environmental changes. This comparison is not rhetorical excess, but a reflection of numerical reality, because the inferred mass difference spans more than an order of magnitude. A blue whale resists currents through sheer bulk while a goldfish drifts with them, and 3 Atlas appeared to switch roles without ever changing its visible outline. Such a transformation challenges intuition, because observers expect physical identity to remain consistent even as conditions evolve. With 3 Atlas, the illusion was maintained by distance and low energy surroundings, where radiation pressure was too weak to reveal the true relationship between force and response. Once 3 Atlas moved closer to the Sun, the same object responded in a way that no longer matched the earlier portrait of enormity. The discrepancy did not arise from faulty instruments, but from assumptions carried forward unchallenged. By framing the problem as a whale turning into a goldfish, the scale of the misunderstanding becomes clear without invoking exotic explanations. 3 Atlas did not change species, but the context changed enough to expose how misleading first impressions can be in space. In that realization, 3 Atlas reminds observers that size in the cosmos is often inferred rather than seen, and inference can quietly fail when the environment shifts. As the implications of the revised mass settled in, a new class of structural interpretations began to circulate around 3 Atlas, centered on the idea that the object might not be solid throughout. If 3 Atlas were instead hollow, or composed of a thin outer shell surrounding a largely empty interior, many of the earlier contradictions would soften without requiring new physical laws. A structure like this could appear large and reflective from a distance, presenting the visual signature of a massive body, while containing far less material than assumed. In this framework, the apparent loss of mass becomes less about destruction and more about revelation. As 3 Atlas approached the Sun, increased radiation pressure and thermal stress could have altered surface properties, changing how light interacted with the object and how forces were distributed across it. What looked like mass shedding might instead represent the gradual removal or transformation of a superficial layer, exposing a lighter underlying structure. Such behaviour is not entirely alien to engineering, where shells, coatings and layered designs are used to manage heat stress and interaction with the environment. For 3I Atlas, a thin outer layer could have served as both camouflage and protection, maintaining stability in deep space, while concealing the true mass beneath. Once conditions changed, that layer may no longer have been necessary, allowing the object to respond more freely to external forces. This interpretation does not claim intention, but it reframes the narrative away from catastrophic loss. 3E Atlas may not have been tearing itself apart, but simply transitioning between states as its surroundings evolved. In this light, the idea of a hollow structure offers a bridge between observation and physics, suggesting that the mystery of 3 Atlas lies not in what vanished, but in what was never truly there to begin with. As efforts to explain the behaviour of 3 Atlas continued, one proposal gained attention, because it seemed to preserve a natural origin, while accommodating extreme observations, the idea that 3 Atlas might be a so-called fluffy comet. In this view, 3 Atlas would be a loosely bound aggregate more like a fragile cloud of dust and ice than a solid body held together by weak gravitational cohesion. At first glance, this interpretation appears attractive because a porous structure could account for low mass while maintaining a large apparent size. However, the deeper this hypothesis is examined, the more contradictions emerge because fragility carries consequences that 3 Atlas never displayed. Objects with such low structural integrity are notoriously vulnerable to tidal forces and thermal stress, especially when they pass near massive bodies or experience increasing radiation. If 3 Atlas were truly that delicate, the journey toward the inner solar system should have torn 3 Atlas apart long before the observed anomalies appeared. Historical examples reinforce this expectation, because fragile comets that approach strong gravitational fields often disintegrate dramatically, leaving behind chains of fragments and expanding debris clouds. 3 Atlas showed no such behaviour, maintaining a coherent point of light and a stable trajectory even as conditions intensified. This resilience stands in direct opposition to what a fluffy comet should exhibit under similar circumstances. The paradox deepens when mass loss is considered because a structure weak enough to lose the majority of its substance should not be strong enough to preserve its overall form. Removing most of the material from a fragile aggregate should result in collapse distortion or visible fragmentation, none of which were observed for 3 Atlas. 3 Atlas therefore appears caught in a contradiction, being described as both extremely delicate and remarkably durable at the same time. In attempting to reconcile this, the fluffy comet explanation stretches itself thin, offering comfort at the cost of consistency. Rather than resolving the mystery, the hypothesis shifts it, replacing one impossibility with another. For 3 Atlas, the absence of expected failure under stress suggests that whatever structure exists is more organised and resilient than a simple cloud of cosmic dust could plausibly be. As alternative explanations were explored, the concept of a light sail began to surface, not as speculation divorced from physics, but as an extension of principles already tested by humanity. A light sail relies on radiation pressure, where photons carry momentum and exert force when they strike a surface, a force small in everyday terms but relentless across astronomical distances. 3 Atlas, when viewed through this lens, no longer appeared contradictory, but instead began to align with a mechanism that naturally links distance, brightness and acceleration. Far from the Sun, radiation pressure is weak, and a light structure can drift quietly without revealing its true nature. In that deep cold environment, 3 Atlas would have appeared inert and massive because the available photon pressure was insufficient to produce measurable motion. As 3 Atlas moved inward and sunlight intensified, the same surface area would suddenly experience a much stronger push, producing acceleration without the need for jets, explosions or internal engines. This behaviour matches the observed pattern, because the acceleration of 3 Atlas increased smoothly, rather than erratically, consistent with a force that scales predictably with solar intensity. Unlike outgassing, which is uneven and chaotic, radiation pressure acts continuously and uniformly across an exposed surface. 3. Atlas therefore exhibited a response that felt controlled rather than turbulent, a subtle but important distinction. The light sail model also resolves the mass paradox without requiring matter to vanish. If 3 at last were thin and reflective, its apparent brightness could mimic a much larger, denser object when observed from afar. As conditions change, the illusion of mass would fade, not because 3 Atlas lost substance, but because the underlying structure was finally revealed through motion. This interpretation does not assert intent or origin, but it demonstrates coherence. 3 Atlas behaves exactly as a light-driven structure would when transitioning from deep space into a stronger radiation field. By invoking a mechanism already grounded in physics, the light sail hypothesis transforms confusion into continuity, suggesting that the strange behavior of 3 Atlas may arise not from new laws, but from familiar forces acting on an unfamiliar form. The behavior of 3 Atlas inevitably invites comparison with a much older question in astronomy, the Fermi paradox, which asks why a vast and seemingly hospitable universe appears so quiet. If intelligent civilizations are common, then traces of their activity should be visible, yet the sky remains largely silent despite decades of searching. 3. Atlas reframes this puzzle by suggesting that silence itself may be part of the answer rather than evidence of absence. Traditional assumptions imagine exploration as loud and conspicuous, relying on powerful radio transmissions or bright signals meant to announce presence across interstellar distances. 3 Atlas hints at a different strategy, one where exploration is subtle, passive, and nearly indistinguishable from natural background objects. A probe designed to endure millions of years might avoid broadcasting altogether, choosing instead to drift, observe, and move on without drawing attention. In this context, 3. I at last resembles not a messenger, but a surveyor passing through star systems the way ocean currents pass through reefs, gathering information without disturbance. A design philosophy like this would favour camouflage over display blending with asteroids and comets to avoid interference or detection. 3 Atlas would not need to announce its purpose if its mission were observation rather than communication.